Hey everyone, and welcome to the internet. So what we're going to be doing in today's lesson is having a look at the three different types of ionizing radiation: alpha, beta and gamma. So to start us off, let's have a quick review on what we did in our last lesson. 4 questions on the screen there that I'd like for you to answer in your books. So I'll give you about 3 minutes to get that done. Off you go. Okay, let's check those answers then. So obviously if you get it right, give yourself a tick, and if you got it wrong, then do make sure you have the correct answer written in. So our first one, the mass number, is the number of protons plus the number of neutrons. Number 2, the atomic number, is the number of protons or the number of electrons. Our third one there, an isotope, has the same number of protons but a different number of neutrons. And then finally, number 4, there should have been 8 neutrons. So add them up, let me know who got 4 out of 4, who got 3 and 2 and 1 in the chat window. So what I've given you on the screen there is a picture of a very famous scientist. Let's see if you can name that scientist in your book. I'll only give you about 10 seconds to write down that person's name. Hopefully we did manage to identify that scientist as Marie Curie. Now, Marie Curie was actually born in Poland back in 1867, and the reason she's quite famous is she was actually the first woman to win a Nobel Prize, and actually the first person and the only woman to have won 2 Nobel Prizes. And she's the only person to win a Nobel Prize in 2 different sciences. So she is really an impressive lady. And the reason that she was so impressive was because of the work that she did on radioactivity. So she actually developed that term first of all and came up with a theory of radioactivity. So what you'll actually find is the periodic table has elements that are named after her too. And what we've actually got is, well, actually about now, there should have been a film called Radioactivity which was released in the cinemas. Obviously, with the cinemas closed at the moment, then I think that's been pushed back for the foreseeable future. But when it comes out, maybe go see it. What we're going to do now then is delve a little bit deeper into these actual atoms themselves. Now, if we think about most atoms, then we can describe them as being stable. So what that means is that they're not going to break down or decay. However, there are some atoms that have what we refer to as an unstable nuclei. So these are the ones that are going to break down, and when they do this, they're going to emit radiation. So any material that emits radiation are described as radioactive. So make sure you've got those 5 sentences written down in your book. I'll just give you another minute and a half to get that done. What we need to know about then are 4 different types of radiation, and they're summarised in that table. Now, you are going to need this table, so by all means make a start on getting that in your books while I talk you through it. So what we have in this table are our 4 types of radiation: alpha, beta, gamma and neutron. Now, what I've given you there are the key bits of information about each one. So we've got the type of radiation it is, we've got the symbol for it, we've got what it really is, and then we've got the equation symbol for it as well. So if we look at alpha first of all, then this is a particle. So we've got the little symbol there for alpha, so I would suggest you practice drawing those as well. Now, in terms of what an alpha particle actually is, it's the nucleus of a helium atom. Now, when we actually write that in an equation, because it's the nucleus of a helium atom, we start off with He, the symbol for helium, and then with the top, the number 4 there, is the mass relative to the proton, and then the bottom number there, the 2, that is the charge on it. So that is our alpha particle first of all. The second one is beta, and again, this is a particle. What it actually is a fast moving electron. Now, hopefully we do remember that the mass of an electron compared to our proton is incredibly small, so in this case we've just given it that mass of 0, and its charge is -1, and our symbol for an electron is a lowercase e. The third radiation we're looking at is gamma. Now, this isn't a particle, this is an electromagnetic wave. Now, we'll find this when we look at the electromagnetic spectrum. This is one of the waves we will find on there. It doesn't actually have an equation symbol because it is just an electromagnetic wave, it's energy. The fourth and final one, the neutron there, that is of course a particle. it's given the symbol of a lowercase n, and it's a particle we find in the nucleus. So when we come to the equation symbol, lowercase n for our neutron, its mass is 1 and its charge is 0 because neutron have no charges. So make sure you've got that table written down. I'll just give you another 90 seconds if you haven't already finished. Next thing I'd like you to do is just in your books, see if you can answer these two questions. What is the nucleus of an atom made of? And where does a beta particle come from? So I'll just give you about 30 seconds to have a go at answering those in your books. Hopefully we remember the nucleus is made of protons and neutrons. Give yourself a tick if you got it right. And the beta particle actually comes from the decay of a neutron in the nucleus. So let's take a moment to have a look at that in a little bit more detail. So in our nucleus we find our neutrons, and those neutrons can actually go through a process of decay in order to make a proton and an electron. So what we can see in the picture at the bottom of our screen there is the purple blob in the bottom left is our neutron, and then it's going to decay in order to make our proton, the red one with the P+, and the grey one there, our electron, which is the beta particle. So we've established the fact that these different types of radiation exist, but what we actually need to be able to do in order to be aware of them is have some way to measure the amount of radiation present. And the way we do this is by using a device called a Geiger-Müller tube or a Geiger counter. And the picture there just shows you what this would look like. So the Geiger-Müller tube is the little black thing in the front, and then you've got your actual counter sitting behind it with the digital number on the screen. Now, when this is actually working and you hold something that's emitting radiation in front of it, then what you actually hear are little clicks. And those clicks that you can hear are tiny currents that we're producing when the radiation is ionizing atoms of the gas that's held within the Geiger-Müller tube itself. So make sure you've got those couple of points written down for me. I'll give you another 30 seconds if you've not got those in your book yet. Normally this is the point of the lesson where we'd get the radioactive sources out and actually have a look to see what happens when we hold them in front of our Geiger-Müller tube and then place different materials in front of it. Now obviously I don't happen to have radioactive sources just lying around my house for hopefully very obvious reasons, but I have managed to get a video of someone doing the demonstration for you. So what we'll do is have a little look at this video just so you can see what we would normally have done. So hopefully that demonstration actually shows you what happens with different radioactive sources when we place different materials in front of them. And what we were doing in that experiment was we were showing the different penetrating powers of the types of radiation. Now we can summarize that experiment down into the diagram on your screen at the moment. And this is a really important diagram. It has come up on previous exam papers, so I'd suggest that you get a sketch of this in your books. Now, what we start off with are three types of radiation that they're going to ask you about. The alpha, the beta, and the gamma there. So alpha at the top, beta in the middle, and then gamma at the bottom. Now, what we've got over towards the right, that first block we hit, that's just a few sheets of paper, or we could replace that with a few centimeters of air. The next one along, we've got a few millimeters of aluminium, And then finally, at the end, we've got a few centimeters of lead or a few meters of concrete. So what we will see, if we look at alpha first of all, then that one is going to be stopped by a few sheets of paper. And in the demo we just watched, you could see that when the piece of tissue was placed, then it did stop that radiation passing for one of our sources. So we can say that one consisted of alpha radiation. For the beta, you can see that actually goes straight through the few sheets of paper, but it is brought to a stop by the few millimeters of aluminium. So beta is stopped by a few millimeters of aluminium. Gamma though, our last one, you can see that goes straight through the paper, straight through the aluminium, and even when we get to a few centimeters of lead or a few meters of concrete, you can see that even though most of it is stopped, there could still be some that's able to get through that. So imagine having a meter of concrete and the gamma can still pass through it. So that has the strongest penetrating power. So what we can actually do is just rank them in order of their penetrating power, alpha the least, then beta, and gamma the most. So I'll give you another minute and a half to get that diagram done if you haven't already. So what we've just got in that diagram then is just a summary about the different penetrating powers of alpha, beta and gamma radiation. Now, whenever we're looking at this radiation being emitted by the radioactive material, it's what we refer to as ionizing radiation. And by ionizing radiation, what we're referring to is radiation that's going to remove electrons from atoms in order to produce these positively charged ions. Because remember, in an atom, it's neutral because we've got the same number of protons and electrons. So if this radiation is able to remove electrons from the atom, we'll have more protons than electrons, which means we have a positive charge. So we make an ion at that point. So get those 3 sentences written down if you haven't already. Just another 30 seconds to get that done. What I've got for you here is a table that just summarizes some key bits of information about the alpha, beta and gamma radiation for you. So we've got the relative mass, their charge, their ionizing power and their range. So if we look at alpha first of all, then this is actually quite a large mass particle. Remember what we said at the beginning, this is a helium atom, the nucleus of one. So what we can see is this is going to have a relatively large mass. Now the charge on it, as we established at the very beginning, is +2. When we look to see how far that can actually penetrate, it's actually only got very short range, because remember, it's not going far. A few centimeters of air is enough to stop it. But it does have a high ionizing power. So that means that if it comes into contact with other materials, then it's very likely to actually knock those electrons off and create the ions. It's very good at doing that. Beta is our next one. Now remember, the beta particle is a fast moving electron, so it's got a very small relative mass. It's got a charge of -1 because it's an electron, and it's got a medium ionizing power and a medium range. The third one on there, gamma, doesn't have a mass because it's just energy. Remember, it's an electromagnetic wave. It has no charge either. It's got a very low ionizing power, but its range is long. So make sure you know those facts about alpha, beta and gamma. I'd suggest you get that table in your books. Now, where we've been talking about this ionizing power, what we're referring to is the ability of those particular types of radiation to cause the atom to become an ion. So in order to do that, we've got to transfer energy to that atom. So the one we've got there with alpha being a high ionizing power just means the alpha particles transfer more energy to the material, and because of that, they then get a short range, because their ability to travel is all down to the energy that they've got. So if they're transferring lots of that energy to materials they're coming into contact with, then that's obviously going to reduce how far they can go. That's why you've got that correlation between the ionizing power and the range there. So 30 more seconds to get those bits written down. Last thing for today then is our plenary. So those of you working up to a grade 5, it's the 2 columns on the left. Those of you working above a grade 5, the 2 columns on the right. So I'll leave this up here for a couple of minutes for you to have a go at those questions. So I'm going to be having a break for Easter, but we'll be back with our next video on Wednesday, the 15th of April. So I look forward to seeing you then. As always, the answers to the plenary can be found on my website, and the link is at the bottom of the screen. You'll also notice that there's a second link on the screen today, which is to a video done by another YouTuber, Gorilla Physics, which is a really nice way to demonstrate these different abilities of the radiations to actually penetrate materials. So check that video out while you're at it.